Okay, I suggest that we start. So thank you for coming this rainy afternoon to Bellevue for the third lecture of the lecture series on enabling technologies for the clean energy transition. Energy is, of course, a worldwide challenge, as we know. There are a number of challenges that we need to face. There's an ever-growing demand, of course, with the growing population and the needs of the developing countries. Also, what we see is that the renewables are increasing and their share is increasing, which puts a lot of constraints on the energy systems. Also, to manage the energy system in the future, we will need more and more also to integrate energy storage into the system to manage it properly. And the business model will also change, and we will not only be consumer, but also become more and more consumers. And this, of course, again, puts a lot of constraints on the energy system, but also gives the opportunity for new business models. And alongside with the prosumer trend, there's also, of course, the trend that we will go for a very centralized energy distribution system to a more and more distributed energy system concerning the distribution of the energy, but also the control of the energy. And another challenge still also is that 1 billion people have today no access to electricity. So worldwide, this is also a challenge that we need to face in the future. And so for going to the next generation energy system, we need to go more and more to a more intelligent energy system, integrating new technologies like artificial intelligence, new communication capabilities, more and more also Internet of Things that will be integrated to process all of this massive data. And this at the end should contribute to the decarbonization by also integrating more and more renewable energy system into the global energy. We become more and more decentralized with energy production that will be closer to the energy consumption. And at the end, we will have not a single large energy system, but a system of systems. And this, of course, put a lot of constraints on control mechanisms and also need, of course, for higher computational capabilities. And as I said, energy become an asset not only for, let's say, the producers, but also for the consumers. And for this, we need new transaction platforms, new ways of trading. And of course, this needs to be fair and secure. And so over the last, let's say, 2-3 years, we have set up in LIST an energy unit tackling these challenges and developing, as we are a research and technology organization, so really trying to develop new tools, products, services that can be brought to the market. And we focus on 6 domains: the battery storage, introducing technology and solutions for the operation and control of battery energy storage systems; energy communities, which in Luxembourg is also a hot topic that is more and more developed; electric vehicles. Of course, if we would have all vehicles electric today, the energy system would not manage it. So we need also to develop new tools to manage these electric vehicle fleets. Active buildings, also to save energy, to make them more energy efficient; digital twins; and finally power electronics. And for this, we collaborate with many national public partners, but also academic partners internationally, and also private companies. And to do this, we have set up already and still further developing a real-time hardware in the loop laboratory, where we can test new concepts, model them in let's say almost real conditions before bringing them to real conditions. And for this, we develop energy living labs, especially focusing on community-oriented batteries that we start to deploy over these months. So the batteries have arrived, and we are now deploying them on site. So really to go from the concept development, testing abilities in the lab, and then testing them in real conditions. And also for Luxembourg in general, also for our department, of course, it's also good to be internationally connected and to have specialists coming to Luxembourg to give their view on the energy system, presenting new developments. And so with Pedro Rodriguez, who unfortunately cannot be with us today, we have developed a conference, a lecture series that will go until May. And so you can already note down the dates, and you find them, of course, on our website if you are interested to participate in further conferences. And also want to welcome all those that are connected through internet. So it's a hybrid conference also today. And also to acknowledge, of course, the financial support by the National Research Fund, which made it possible to attract so many high-level speakers to Luxembourg. And today we have the pleasure to welcome Julio Romero Agüero from Quanta Technology, who is working in North Carolina, USA. So he is Honduran origin. I don't know if you have also this nationality, probably yes.
Oh, US, yes.
And so he did. He worked, let's say, for a national energy company. Then made his PhD in Argentina in 2005. Then went back to Honduras to work for the National Energy Commission. And since 2007, he is working for Quanta Technology and different positions, and is presently Senior Vice President of Strategy and Business Innovation. So he knows what has to be done to make our energy system efficient and prepare it for the future. And this also, he has contacts with academia, and is a young professor at University of North Carolina at Charlotte to also support PhD students and so on, and the academic system to make the link between academia and the private sector. He's also very active in IEEE. I will not go through all the different positions that he holds presently or has held in the future, but so also a very active in the service to the global community in the energy. And so he will talk to us today about the grid modernization towards smart systems for the clean energy transition. But before giving him the word, I will already take the opportunity to announce the next session that will be on November 14th on hydrogen fuel cell electric vehicles and outlooks in the context of the clean energy transition by Professor Fei Gao, who worked at the CNRS in France. So for those interested, please write already down this next agenda. And with this, I give the floor to Professor.
Thank you. Well, good afternoon. Thank you for joining us today. It's a pleasure to be here. Thank you for the invitation. I was going through the list of previous speakers, and it's truly an honor to be in that list. I have some friends in that list, and I know that they are very respected professors and professionals in general. So the topic of my presentation is grid modernization. It's something that I have been doing for the last probably 15 years, basically since I joined Quanta. So we'll talk about the experience, especially in the US, and I think that there are some potential lessons learned that could be useful here in Europe and specifically in Luxembourg. My presentation is going to be different in the sense that you will not see equations. There are not going to be equations at all. So my work is with the industry. So it's basically what I'm going to present is a summary of experiences working with, especially with electric utilities in North America. I couldn't be here in this room today without the support from my employer. As Lucian mentioned before, I work for Quanta Technology. We are mainly a consulting firm, and the company was founded in 2006. We work very closely with electric utilities, all the large electric utilities in North America, what we call IOUs, investor-owned utilities. And I would say mainly consulting is what we do, but we also develop hardware solutions, software solutions. We also do testing of advanced technologies. We recently launched a spin-off of our company. The name of the company is Innoversa. It's a mobile battery energy storage solution, or mobile DR solution provider. And we have offices in Raleigh, North Carolina. That's where the headquarters are located. And we also have offices in Chicago, in Toronto, in Canada, and 2 offices in California, Northern California, in the Bay Area of San Francisco, and another one in Southern California. And we are a wholly owned subsidiary of Quanta Services. Quanta Services is a very big firm, a Fortune 200 firm. It's a conglomerate of over 200 companies. Most of them are what we call EPC, engineering, procurement, and construction firms. Quanta Services is the largest services provider for the electric utility and gas utility industry in North America. And out of that family of companies, Quanta Technology is the one that does consulting, so it's the technology division. So that being said, so again, I also have a role in IEEE. As you know, IEEE consists of technical societies. So my role is with the Power and Energy Society. I'm vice president of chapters and membership. I'm finishing my last term in December of this year. And this invitation to participate in this event is also through the Benelux chapter of PES. And of course, Pedro is the chair of that chapter. So thank you again for the invitation. So let's start with our presentation. And let me mention some terms that are related to some extent. I'm sure that you have heard about them. Smart grid is one of them. Well, grid modernization is another one. Utility or grid of the future is another one. And all of them are interrelated, and sometimes they are used interchangeably. Sometimes people refer to smart grid as grid modernization, etc. And there are some subtle differences, but the bottom line is that all of them have something in common, which is this vision of operating the grid, especially the distribution grid, in real time, having visibility of every single node in the grid and control as well of the majority of the grid, which is something that we couldn't do in the past. In the past, most of the investments were directed to the bulk power system, generation, transmission, and then distribution was kind of left behind. Over the last 15 years, that has changed tremendously. And now I would say that most of the action is actually in the distribution grid. So these concepts, the vision is that to be able to operate that distribution grid like we do in for instance, in an industrial plant. As you know, in an industrial plant, everything is automated. You have control over every single device in the plant, and you have visibility, right? You know what is happening in real time. So that's the vision. Of course, to get there, it's not easy. We have been going through this transition for 15 years already, but we have made a significant progress. So one way to describe that vision is this diagram that we have here. It's actually, this is work that was published a few years ago with a colleague from University of Denver, Nicole colleague of mine, Ralph Cielo. So, the way we see this is basically think about the utility and the grid of the future as a collection of layers. We have a layer right here that we call the foundational layer. And that is where we have all the foundational infrastructure, where we have standards and models, the business and regulatory side of things, the human resources side of things as well, and processes. So I'll give you an example. Why is this important? So let's talk about foundational infrastructure. A lot of grid modernization and smart grid, etc., is about deploying technology, sophisticated devices, advanced devices. But you're not going to deploy those devices on top of deteriorating or aging infrastructure. You need to address the foundational infrastructure as well. So I'll give you an example. Let's suppose that you deploy distribution automation equipment and you do it on top of old wood poles. Then there is a strong storm, the pole breaks down, and the wonderful recloser, your microprocessor-based advanced recloser, falls to the ground. It doesn't matter that it's a sophisticated equipment, it's not going to do anything, right? So you have to address the foundational infrastructure, and a lot of the initiatives around resilience and weather hardening are related to replacing that foundational infrastructure. Then on top of that, once you have done that, on top of that, you look at the enabling layer. This is enabling technology. So this is incremental intelligence. Why incremental? Because, well, it's not like the grid is really dumb. There is some level of intelligence, where relays is a good example, or voltage control and regulation, load tap changers, capacitor banks, technologies that we have used for a long time. So there is some intelligence. What we are trying to do is to increment that intelligence and to deploy some enabling infrastructure like telecommunication systems, right? So that's what you do once you address the foundational infrastructure. Then on top of that, you look at applications, and this is where all the analytics are located, the real-time monitoring and control, and also, very important, the interaction with end users. This is where all of this is enabled by the previous two layers. This is where you have all of those sophisticated big data analytics where you process AMI data and PMU data and all of that. And then on top of that, you have an innovation layer. And why is that? That is very important too, because the grid is going to continue evolving. We are just beginning, right? It's a journey. So we need to continue doing innovation. We need to continue doing R&D, pilot and demonstration projects. And I'm talking about from the point of view of the industry. The industry needs to, of course, academia continues doing research and innovation, but industry also needs to do the same. And the collaboration with academia is very, very important. Academia, vendors, consultants, the industry. And once you have those four layers working together, you can see that there are some feedback loops and relationships between the different layers. Once you have those four layers working together, then you can talk about a utility or grid of the future. Now, why is all of this important? Well, why do we need grid modernization? The reason is, well, the grid is changing. The key driver behind that change, in my opinion, is the adoption of distributed energy resources. I mean, what are we doing today that we were not doing 20 or 30 years ago? And it's precisely distributed resources. 20, 30, 40 years ago, I remember when I started my career, it's been close to 30 years. I used to work for a utility in Honduras. And I remember we had some distributed generators. Actually, I was responsible for the distribution grid where we had one small hydro, 1 megawatt small hydro. And so we had that technology already, but it was a very special case. And I remember that we used to deal with that generator. It received a lot of attention, let me put it that way. Today we have thousands of those. Sometimes in a distribution feeder, we may have hundreds of small, or thousands sometimes, of small generators connected to the grid. So that's the main driver so far. Now the adoption of electric vehicles, the electrification of many of the things that we do, for instance, heating systems, that is going to create a second wave of significant change. So that's what is changing. Now, why is that important, and why do we need grid modernization to integrate those distributed resources? So this is a good example. This is actual data. This is from Hawaiian Electric, from the island of Oahu. This is a service transformer. In the US, we use, it's very common to use single phase transformers. And this is, I think that this is a 37.5 kVA transformer, single phase. This is typically used in residential areas. So, so what we have here is, this is the load or the power flow through that service transformer. This line right here, whatever is above that line is traditional load flowing downstream from the transformer to the end users. Whatever we see right here is what we call reverse power flow. So you can see, it's very easy to see here. This is a kind of a Gaussian function, right? So what they have in that neighborhood is photovoltaic, PV technologies, right? PV distributed resources behind the meter being served by that transformer. So during around noon every day, the amount of PV in that neighborhood exceeds, the output from those PVs exceeds the load, the local load, and then the transformer starts exporting or injecting power to the grid. It happens, you see, every day. Some days are cloudy, some days are very sunny, and the rest is basically kind of typical. There is a peak in the evening, etc. So this is new. This didn't happen before, right? This again, and we have now thousands of these meters. So you would say, so what? I mean, yeah, it's new, but what's the issue with it? So this is the issue. Now let's look at voltage. Again, this is real data. So in the US, we use 120 volts to 140 volts is for single phase residential service. And there is a range, of course, around 120 volts that is defined by the ANSI standard C84.1. And basically what it says is that voltage shouldn't exceed 126 volts, okay? So the purple line shows you that, yeah, actually during noon, it's completely correlated with the reverse power flow from that service transformer. Voltage exceeds that limit. And now we are able to see this now because we have AMI, we have smart meters, we have sensors, etc. If we didn't have that, the only way to figure it out would be a customer would complain probably, hey, what is happening with my, my home? Lights are very shiny today. The issue is that, well, you're not in compliance, and this may create, in the long run, it may create some issues with end user equipment, right? Some loss of life and some issues. So, okay, so there is a problem right there that we need to correct. How do we do it? We'll talk about that in a moment. Remember, this is service transformer, so basically low voltage. Now, the problem is not unique of low voltage systems. It happens at medium voltage, at distribution system level. So this is from another utility. This is Dominion Energy in Virginia. This is a substation, a medium voltage substation. In the US, we use what we call 15 kV class, typically for distribution, medium voltage distribution. So it would be the equivalent to, I think that here in Europe, it's very common to use 11 kV in distribution, right? So this would be the equivalent. 13.8, we use 12.47 kV, 13.2 kV, that type of voltage. So in this case, the situation is somewhat similar. The area in pink is reverse power flow. The area above that line is forward power flow, the traditional forward power flow. So you can also see the photovoltaic, that photovoltaic is driving, in this case, that reverse power flow. And there are sunny days again, and there are not so sunny days, right? Cloudy days. So I would say if we were able to predict, and if we knew that every day it's going to be smooth, kind of Gaussian function, right? That's going to be the output from a PV plant, which is somewhat similar to what used to happen with small hydros, then things would be easier. Yeah, there would be a need for change, but things would be easier. The challenge is that we cannot, I mean, it's very difficult to predict. And that variability creates voltage fluctuations and impacts also equipment, voltage regulation and control equipment. So we need to do something about that. So we'll talk about it in a moment. Okay, so we talked about low voltage, medium voltage. Now let's look at the bulk power system, okay? So this is California, the California ISO system. And to put things in context, if California were a country, it would be one of the probably top 5, or surely one of the top 10 economies in the world. I mean, it's a very big state, a very strong economy. So, so what we have here is really, I mean, in my opinion, this is amazing. In a matter of 80 years, 2015, and then we have 2023, the load curve in the California ISO system has changed dramatically. So in 2015, there was adoption of wind and solar, but still the load curve resembled what we are used to seeing in traditional systems, right? But California has a very aggressive, very progressive renewable portfolio standard. It's basically a government mandate to adopt renewables. The goal, if I'm not mistaken, I think that it's like 20, I'm trying to remember if it is by 2045 or 2040, but it's around that time. 100% of the energy delivered to end users have to come from clean energy technologies. And so they started adopting wind and solar very aggressively. And you can see that every year that value, let's call it valley, was increasing and increasing and increasing. And then I think it was in March of this year, if I'm not mistaken. I think this is from March of this year. You can see that basically the demand at this time of the day around noon, when you subtract the total, what we call utility scale PV and wind from the demand of the system, we ended up in negative territory, right? So I mean, a significant change. This used to be called the duck curve, and now they call it the canyon curve because it looks like a canyon. So this is, again, very new. And for those of you who work in operations, you know that load follow, to be able to follow this very fast ramp with inverter-based technologies, or even with some of the traditional technologies, is very challenging, right? So another need for modernization, right? For changes in the way we do things. So I mentioned renewable and clean energy standards, and it's important to make a difference between both of them. Yes, certainly, renewables are clean energy technologies, but clean energy technologies include more technologies. So, and that definition varies sometimes from country to country, and even within a country. In the US, we have a federal system. So every state is like a small country. So for some states, I'll give you an example, natural gas may be considered a clean energy technology, yeah. In other states, it's not. Some states talk about clean coal, others, yeah, clean coal, yeah. Other states, they don't, right? So, and this can also include carbon capture and other things, right? And for some states, I think that all of them, most of them agree on nuclear being clean, but for others, California is actually, California had a plan. I think that they are reevaluating it now, of closing all nuclear stations. So it varies, right? But the point that I wanted to emphasize here is that it is a clear trend. More and more states in the U.S. and of course countries all over the world are adopting this either renewable or clean energy technology targets. And that's great, but in reality, think about it. We have never operated a system of this magnitude. The US system has a peak demand. Well, we have several time zones, so that makes things complicated, and two different systems, well, three different systems, the Eastern Interconnect, Western Interconnect, and ERCOT. But it's roughly 800 gigawatts. I mean, it's a massive system. We have never operated a system of that size purely with renewables or clean energy technology. So there is a significant change. Yes, we have operated islands and even countries. I mean, here in Europe, you have that experience. But I was talking to Pedro the other day, and I was mentioning. So to give an example, Denmark, right? Denmark has achieved that type of goal before, but they are interconnected to an infinite bus, right? That takes care of regulating voltage and frequency. So that facilitates things, right? It's different when you have to do it yourself. So it's quite a challenge, and that requires, again, modernizing the grid, using new technologies, and to be honest with you, develop knowledge that's new knowledge, right? Again, we haven't done this before, so this is going to require many of you to contribute. We have realized that, yes, I mean, if you want to achieve those aggressive goals, you also need energy storage, right? Because remember, these are variable generation technologies. So you need energy storage to stabilize, quote unquote, stabilize the grid. So more and more states in the US are adopting also energy storage mandates. And here are some examples: California, Nevada, Oregon, and then in the East Coast, New York, Virginia, and others. It's a very important topic. Energy storage is a very important topic, but the challenge here is, as you know, energy storage technologies are, the battery-based energy storage technologies, they have a limited energy or time, in this case, limit. It's not like pump hydro, right? But pump hydro, of course, you cannot build pump hydro everywhere. That's the beauty of batteries, that you can distribute them, but they have a limited capacity. So there is a lot of interest, plenty of discussion on what is called long duration energy storage. So more than just a few hours, ideally a few days. And that's part of that new knowledge that I was mentioning before that needs to be developed. So going back to grid modernization, now that we understand that concept, so what is included in grid modernization behind that, besides that vision about operating the grid in real time and all of that, is basically addressing some key features. Some of these features have been around since the beginning of the industry, others are new. So which ones have been around since the beginning of the industry? Well, safety is one of them, right? Of course, we always have wanted a safe system. Reliable is another one. Let's see, accessible, right? Everybody should have access. And affordable, of course. All of these, all of the things that we have been discussing are easy to do when you have unlimited funding. But the reality is that we don't have unlimited funding, so we need to optimize. So affordability is very important, because at the end of the day, that funding comes from taxes and also from rates, right? So end users have to pay for it. So, but again, all of those requirements have been around since the beginning of the industry, but there are new requirements. The grid needs to be resilient. Why does it have to be resilient? Because we have been experiencing, or we experience it every day, climate change, right? Climate change is affecting all of us. And a moment ago, we were talking about low probability, high impact events. And I would argue that high impact remains high impact, is true, but that low probability is now becoming not necessarily low, more frequent and more severe weather events, and we will talk about that. So we need to be ready for that, right? So the system has to be resilient. Especially in the US, we are impacted by major weather events often. We call them $1 billion events, the amount of damage that they cause. And then when you look around the world, the situation is similar. So a good example would be what happens in Pakistan, what happens in Australia with the bushfires, or this year it happened in Hawaii as well. So it's wildfires, hurricanes, flooding, etc. Another new requirement, of course, we talked about, it has to be clean, it has to be secure, and by secure, operational security for sure, but also cybersecurity and physical security. Physical security is a big concern in the US. The potential for sabotage and those type of issues. And as you can see, the grid is now is going to rely a lot on renewable technologies, variable technologies, so it has to be also flexible, it has to be adaptable. And that includes, let's see, the ability to operate with those type of technologies, and also the ability to reconfigure potentially to be more resilient and to be more reliable. So grid modernization addresses all of this, and it does it through what we saw before, through foundational infrastructure, through deployment of technologies, to modernizing processes, and we'll talk about also the human resources side of things, because that also has to evolve. In the past, and we'll talk about it in more detail, in the past, the typical utility engineer was somebody with a degree in electrical engineering and maybe some orientation to power. And that remains true. But now you need to know about telecommunications, about power electronics, about data analytics, about control. So it's a broader, a different type of profile. And then we have the challenge of there are not enough of us, right? I mean, there is a shortage of that. Now, so grid modernization is something that is happening all over the world. And this is just an example of the 40 largest electric utilities in the world. Some of them in North America, some of them in Europe, some of them in Asia Pacific. And the different areas in which they are active. You can see that DER is it goes kind of across the board. Electric mobility, that is especially strong in Europe. It's becoming also strong in Asia. And finally, in the US, the last, I would say, 3 years is really impressive. I mean, it's finally happened. And there are other aspects too, smart homes. So all of this modernization that is happening in the grid is starting to happen also behind the meter. So now we have, let's see, the fact that we have energy storage, photovoltaic, and also electric vehicles behind the meter create some opportunities to optimize, to even provide services to the grid, and also to improve reliability and resilience. There are utilities that are doing that already. I was mentioning Green Mountain Power, which is a utility in the Northeast in the state of Vermont, if I'm not mistaken. They have partnered with Tesla. They have deployed Tesla power walls behind the meter, and they are using those Tesla power walls. They are basically operating a sort of virtual power plant for peak shaving. So they are able to shave the peak of their system, and that creates some economic benefits. In the US, more specifically, when utilities talk about grid modernization, sometimes they have a kind of a flagship initiative or technology that they implement. For some of them is AMI. For others is automation. For others it's more about the foundational infrastructure. So these are examples of some of those projects for several different utilities in North America. So the point here is that it is real. I mean, this is happening. This is a summary of regulatory filings by those utilities. And a regulatory filing is necessary. All of these utilities are private companies, but they are regulated because they have a natural monopoly. They operate a natural monopoly, in this case, the distribution grid. So they have to justify investments. When they want to make an investment, they have to request authorization from the regulator. So that's what is called a regulatory filing. How do you do grid modernization? So this is very interesting because for many utilities, they started doing it organically. Basically, they saw a need here, a need there, and they started implementing solutions. And that is a good way. I mean, you can do it that way. It's not the most efficient way because there are synergies sometimes between initiatives, and sometimes actually there are they may obstruct each other sometimes. So the most efficient way to do it is to create a roadmap, which is kind of a master plan. Once you define a vision and a target or targets, then you develop a plan, you identify a portfolio of initiatives to modernize the grid, you develop a schedule, and then you start implementing. When you develop that grid modernization roadmap, you also identify benefits and costs, because remember, you have to request, if you work for a utility, you have to convince the regulator that those investments are justifiable. So you have to identify benefits and you have to identify costs. Those benefits, some of them are tangible, monetary benefits. In other cases, they are qualitative benefits, strategic benefits in some cases. You try to quantify them to assign a monetary value to all of them. Sometimes it's not possible. So, but you have to list them at least. Sometimes they are savings, and those savings can be related to reduce O&M operations and maintenance. In some cases, it can be related to deferring capital investments. So you basically look at that side of the equation, and then you go to the regulator and you say, okay, this is what I plan to do. This is what it's going to cost me, but here are the benefits for the utility and more importantly, for end users. So this is basically what we have here. And something that is also very important is to look at the interdependencies between the different initiatives that you're going to propose. And by initiatives, I mean, yeah, deployment of AMI, deployment of sensors, deployment of an ADMS, deployment of substation automation, etc. That's what I mean by initiatives or programs. You have to look at an interdependency analysis. And what that means is, especially when you schedule, is very important. I'll give you an example. Let's suppose that you're going to deploy distribution automation, Flisser, which is a very popular technology. And let's suppose that the solution is a Flisser that is based on a telecommunication solutions. So that means that you have to implement first telecom and then automation. You cannot do it the opposite way. So that interrelationship is important, that interdependency analysis. So you can schedule correctly. And these are examples of some of those extracted from some of those filings, of some of the benefits that are typically claimed in those regulatory filings by the utilities that I mentioned before. And this is the benefit cost ratio that has been reported by some of these utilities. Now, you can see that most of them are greater than 1. What that means is that benefits, once they are quantified and assigned a monetary value, exceed costs, which is good. That's what you want. You want to receive more than what you invest. In some cases, you can see that they are under 1. So that means that quantifiable benefits are less than cost. But that doesn't mean that you're not going to file your plan, because there may be some qualitative or strategic benefits that you have to document, and you have to consider in your plan, and still you have to try to make the case with the regulator. Now, those benefits are real. If you develop your plan right, you're going to receive those benefits, and this is real data as well. It's a good example from Florida Power and Light. So this utility is, I think that is the largest utility in the state of Florida. So they provide service to probably the majority of the state. So that is an area that is prone to hurricanes, right? Florida and flooding, etc. So in 2005, they were impacted by Hurricane Wilma, a Category 3 hurricane. Winds, maximum sustained winds of above 120 miles per hour. Remember, 1 mile is 1.6 kilometers, right? So very strong winds. So as you can see, they had quite a few customers impacted, and most importantly, the average customer outage had a duration of about 5 days. Think about it, 5 days without electricity. A lot of damage. It was really, really bad. So they decided, okay, enough is enough. We are going to modernize our grid. We're going to improve resilience, reliability, etc. They started investing. They invested billions of dollars in strengthening the grid and modernizing it, etc. Then, of course, hurricanes happen often in Florida, but they were lucky for a few years. But in 2017, they were impacted by an even stronger hurricane, Category 4, and winds exceeding 130 miles per hour. And because of those investments, partly because of those investments, you can see that the average customer outage was basically cut in half, right? It decreased under 50%, 40%. And they had several, I mean, the majority of their system was impacted one way or another. Customers were impacted, but the average duration of those outages was decreased significantly. So this is a good example of those, how those investments can improve resilience in this case and reliability out there. You can see that SAIDI score. SAIDI is basically it measures the average duration of service interruptions impacting an average customer in the system. You can see that it decreased over those years from around 80 minutes to 45, so a significant improvement. And here are some examples of those grid modernization programs that we talked about some of them already. Some address foundational infrastructure like hardening. And by hardening, what we mean is a fair amount of the distribution lines in the US. I think that the average for the country is around 80% of the distribution grid is overhead. So that's different than here in Europe. So the majority of the grid is overhead. So we use, traditionally we have used wood poles, and they are divided by or categorized by class. So, typically a class 5 or class 4 type of pole. That's what it was used in the past. And now we are using class 1 or class 0. That means they are more robust. I mean, very strong poles. When we use wood, or we are using concrete or polymer or other materials, so those poles are now stronger. So that's what we mean by hardening. It can be also underground in the grid strategically, because if you want to underground the entire grid, we will be talking about massive investments that end users are not willing to pay for, or regulators are not willing to approve. So it can be done strategically in areas that are really vulnerable, and then the rest you can harden the grid. But that's just one example, foundational infrastructure. On the technology side of things, it can be things, well, I mentioned real-time operations already, or advanced protection, automation and control, can be analytics. It can be advanced planning, very important. Planning this new grid requires developing some new concepts. One of them, just to give you an example, would be DER hosting capacity. And what that means is you have your grid. Let's suppose that there are no DER at all. There is no DER at all. And then you want to estimate what is the maximum amount of DER that I can interconnect to that grid without impacting operations performance. So you calculate that and you use that as a reference to identify investments. If you want to integrate more DER, then you need to strengthen the grid, you need to make investments. So new planning approaches. And so this is more related with processes, others with technology, and others with foundational infrastructure. And the idea is basically to transition from something that looks like this, or used to look like this, into something that looks like this, with, you see in the past, one-way power flow, now two-way power flows, smart meters, sensors, automation, automation in the distribution grid and also in substations, and even things like fax devices. Probably you have heard about fax devices. Basically, power electronics based, very sophisticated devices, beautiful devices, expensive, that traditionally have been used in transmission only. Now they are being used in distribution too. There is a low voltage SBC, static bar compensator, that is becoming very popular in the US at least. It's a technology developed by Verint. I think that I have another slide later. So even that, to be able to control voltage at end user level. This is something that Hawaiian Electric has deployed, San Diego Gas and Electric and others. And this is an example of going back to Florida Power and Light, a comparison between what they did in where they were in 2005 when they started that transition and where they were in 2021. So they continue making investments. So you can see they were doing strategic undergrounding, right? 39% of the system was underground at the time. In 2021, it was 44. So it wasn't massive undergrounding, it was more strategic. Pole inspections, vegetation management, intelligent devices, using concrete or steel in transmission towers instead of just wood, so they increase that. Making sure that some of their facilities are now protected against flooding and so many different things. But you can do much more than that. I mean, they have been doing a good job, but you can improve resilience in so many different ways. And this is a busy slide, but basically what we are saying here is that resilience has so many different dimensions. And some of those dimensions are not about the grid itself. Many of them are, but some are not. So I'll give you an example. This one, logistics, staffing, and processes. So the pandemic was an excellent example of one of those low probability, high impact events. So during the pandemic, some utilities, what they did is they named it sequestration of operators. What that means is that, think about it, let's suppose that with COVID, right, and especially in the early days, one operator, system operator, right, bulk power system operator, gets sick, and then the second gets sick, and you see, 5 of them, all of them get sick at the same time. Who is going to operate the grid, right? So what they decided to do was to, in some cases, they asked them to, okay, don't go home, stay in this confined environment in the control center. We'll bring you everything that you need. Don't go anywhere. Nobody goes in, nobody comes in, nobody goes out. So that they called it sequestration, and in that way they made sure that nobody got sick and that they had somebody to operate the grid. So that's just one example. So it's not necessarily about the grid; it's about processes. So yeah, it has multiple different dimensions. And very important here, it has a relationship also with other critical infrastructure. The electric grid is, let's say, critical infrastructure, as it is telecom and gas and IT. And why is that relationship important? I'll give you an example. In Texas, we had a major event in 2021, Winter Storm Uri. And basically let's see, for Texas standards, it was a very cold winter combined with snow, and that is not common in Texas. I mean, it gets cold, especially in the north, but in the south and southeast, it doesn't get that cold, and we usually don't have snow. So some of the plants were not ready for that. They had not been winterized, so they couldn't continue operating. But other plants that were winterized, they couldn't continue operating because they were natural gas plants, and the natural gas suppliers were affected in the same way. Their pumps and their facilities were not winterized, so they couldn't provide they couldn't deliver the gas that was needed to power some of the gas turbines. So you see, there is a very close relationship between critical infrastructures. Telecom would be another one. Think about one day, you know, the electric grid may be fine, but the telecom provider, if they use a telecom provider, one day says, I'm sorry, but we have a blackout, or there is no internet or whatever. So it's important to look at that relationship with other critical infrastructure when we talk about resilience. Undergrounding is a big initiative, strategic undergrounding in the U.S. To improve resilience, and some utilities have proposed actually quite ambitious programs. PEN is one of them, but more recently, the last month or so, there are some issues about this. The Commission is questioning the need to underground this amount of miles of power lines to improve resilience. In their case, they have issues with wildfires. Another utility in Southern California is proposing, instead of using undergrounding, to use aerial insulated cable, aerial bundle conductor, and other types of insulated cable. The idea is to, if there is contact from vegetation, to prevent an arc, because that arc can create a wildfire. Quasar is a program that is very common for some utilities. When they talk about grid modernization, they talk about FLISR, which means fault location, isolation, and service restoration. And it's basically what FLISR does is to automate the outage management and restoration process. So when there is a fault in the grid, usually the distribution grid is meshed. So it's a mesh, but it's operated radially. So feeders they have normally open points, connections, but normally open points with neighbor feeders. They are not networked like the transmission grid. So typically what happens is when there is a fault in a feeder, so the idea is you isolate, you use equipment like switches or reclosers to isolate the faulted area, and then you reconfigure the grid using neighbor feeders so you can restore service to other clients. That process, if you do it manually, and that's how it used to be done in the old days, it can be time consuming. Locating the fault, patrolling the line, opening devices, closing devices. And what FLISR does is that it automates that process using advanced relays and reclosers and telecommunications, etc. And instead of spending hours, right? Sorry, here it is. Yeah. So instead of spending hours, for instance, in travel time and patrolling, all of that stuff, then in a matter of minutes, sometimes you can restore service and you have isolated the affected area. So the savings can be from hours of interruption duration that can become a matter of just minutes. So it's quite effective. So that's one of those flagship programs. So you can see here, without Fleecer, power is restored to customers on healthy sections of a feeder. And this is just an estimated example, for instance, in something around 1 hour, right, between 45 and 35 minutes. But then if you use Fleecer, then in less than, around 5 minutes, everything is restored. I mean, those customers were located in healthy sections. And when you use Fleecer, that improves reliability. It can improve reliability significantly, which is shown here. Basically, what we have here is this is a real feeder, and that feeder had a couple of neighbor feeders, normally open points right here, normally open points, connections to neighbor feeders. And so initially there were no reclosers at all. I mean, there were some other devices, but not reclosers. So what was simulated here was to deploy to normally open reclosers here and to normally close reclosers here, one to protect this branch of the feeder, another one to protect this other branch of the feeder. And then by doing that, reliability improved significantly in those areas, because when you lose the grid, when there is a fault upstream from these devices, basically what happens is that this device open here automatically, and this one closed. So this branch is now supplied by this neighbor feeder, and in this case, the same thing happens. So this one opens and this one closes, and then this branch is supplied by a neighbor feeder. So in the figure on the right, this was reliability before on the side. The areas in red means poor reliability. The areas in green means good reliability. So now with the installation of automation, you can see that reliability improved significantly. And this is another, this is a real system, the downtown area of one of the most important cities in the US. Same thing. So through the deployment, we have around 100 feeders here. Through the deployment of Fleecer, the simulation showed that there was an improvement in reliability. Basically, you see more red and pink and orange here, which is poor reliability, and you see less on this side, better reliability, more blue, more green, more light blue. There are still some pockets here of poor reliability. Why is that? Because in those areas it was concluded that it was not cost effective to improve reliability, so the utility decided, yeah, we're not gonna do it. We're not gonna do it in that area. Modernizing substations is another grid modernization initiative, and the term digital substations is a very popular term these days, and it's basically what is shown here is ensuring that substations are ready for the integration of renewables. In some cases, it includes the deployment of energy storage in substations to do things like peak shaving or to do intentional islanding, and again, to improve resilience and reliability, to pay a lot of attention to power quality, deploy advanced sensors, power quality meters, PMUs, deploy fiber also, so you can monitor and control in real time. Use IEC 61850 for automation, and a lot about analytics, to be able to use all of that data to analyze assets, the performance of assets, and also optimize maintenance and asset management in general. So it's a lot about analytics and a lot about real-time monitoring and control. Let me skip this. So this is important now that I mentioned analytics. So in the past, to do analytics was difficult because we didn't have enough data. but that is changing. It's changing quickly. Now, actually, in some cases, we are overwhelmed by the amount of data that is available. And data alone is not good enough. We need information. We need to process that data. So analytics allow you to do that. I think that most utilities are good at doing this, what we call hindsight analytics, which is to look at the past and describe what happened in the past. So reliability indices is a good example, right? So you collect data, you process it, and then you say, well, the performance of this substation or this feeder was worse than this other one, etc. These are the areas with good reliability, bad reliability, etc. Next step is diagnostic, which is root cause analysis, and we are good at that. So events happened already, we collect data and we analyze it. We are good at that. The more sensors you deploy, the more data you collect, and the more granular all of that is, then so what happens then is you start discovering new things. So a good example was the service transformer case that I showed you at the beginning. In the past, without smart meters, that utility wouldn't have been able to know that there were some voltage violations. So discovery is the next stage. And this is the fun part. And this is where we are studying, it's a journey as well, predictive analytics. So what does that mean? We collect data, we analyze it, and then we start identifying patterns in the data. And that is especially true when we collect fault current oscillography. That's one example. So when you collect fault current oscillography, you notice that, well, when the fault is caused by defective equipment, there is a fault current signature. When it's caused by, and within faulted equipment, it depends on the type of equipment. If it is an insulator, if it is deteriorated insulation in a cable, etc., the patterns are different. And the patterns not only when the fault occurs, but also before, more importantly, before the fault occurs. When there is a tree touching a line, a different type of pattern, etc. So what utilities are doing is collecting all of this data from advanced sensors, fault circuit indicators with that capability, and they are starting to analyze those patterns and identify patterns, precursors that are precursors of a fault. So then as you monitor in real time, when you start seeing those patterns, then you can infer that a fault may occur in the future in a specific location. So that is what predictive analytics does. And so we're starting to get into that. And then we have prescriptive analytics, which is, okay, so I have identified a pattern in the system that indicates that something may happen. What do I do about it? So I can use analytics also to identify those solutions. And then we have cognitive analytics, which is more related to using AI. How do we use AI to optimize what we do? So it's again a journey. And there are additional technologies that are shown here. PMUs is one of them. Phasor measurement units, and more recently, waveform measurement units. And these devices allow you to measure, well, phasor measurement units are important now because we have generation in distribution. In the past, we didn't have it, so it was not necessary. PMUs have been deployed in transmission for a long time. Now they are becoming more popular in distribution. Waveform measurement units are used for power quality monitoring, going beyond just substations or feeders. And then the concept of reclosing is also now used in sub-transmission lines. That is somewhat new back in the US. PMUs, well, I think that I talked about this already. What I can tell you is that the number of deployments in the US has increased significantly to the point that now we are looking at distribution rather than just transmission. Here are examples of some of those sensors and technologies that, I mean, these are real, these are commercial products that you can purchase This is the advanced sensor that I mentioned before that has that oscillography capability. So you deploy this. This is developed by Sentient Energy. There are thousands of them deployed in distribution lines. They collect data, and utilities like Florida Power and Light are using it for predictive analytics and all of that stuff. This is the equivalent for an underground system. Then other type of sensors. This is for low voltage. This is for medium voltage. This is a distribution PMU, well, power quality meters. This is the FACS device that I mentioned before, the low voltage SVC, another type of sensor, in this case for underground grids. This one is a very interesting one. It's a recloser for single phase service transformers. So you install it on the primary side of service transformers instead of fuses, and it has that reclosing capability. So it's a somewhat new product. And this one is to measure. It's basically it allows you to measure with the same meter energy consumption and energy production from end users that have behind the meter this is an example of a real project. In this case, this is deployment of PMUs. There are a couple of PV plants in this distribution feeder, the substation. This is the feeder. There are some capacitor banks, a couple of PV plants, and then the locations in blue is where PMUs were deployed. And this is the data extracted from PMUs. What is the beauty of PMUs is that you collect data and it's geo-referenced, right? It has a GPS and it's synchronized, time synchronized. So you're truly measuring the state of the system. In the past, using, or even today, using just conventional sensors, the challenge is the latency of, let's see, the telecom means. And if you have several different technologies and if you have several different locations, then measurements are not coordinated, are not time synchronized. With PMU, you can do that. Recently, we completed a roadmap on applications of PMUs in distribution systems. This was a project that was done in collaboration with the Department of Energy and Oak Ridge National Laboratory, and also a couple of utilities, and the gas and electric was one of them. It's available, by the way, it's available online. So I think that, yeah, right there. In that link, you can just click on that link and you can download it. It's available online. FACS devices, I talked about this, and very well known in transmission. We are using more and more in distribution. This is from Hawaiian Electric. This is one example of that low voltage SVC, how it was applied to solve a problem. The name of that product is an ENGO. That's what you see here, ENGO, angle off, angle on. So what they did here is, okay, the ENGO is deployed, but it's off, right? And here is the PV plant production. And then this is what was happening with voltage in that specific location where the angle was installed. So there was a higher voltage fluctuation range. Then the angle is on, so the angle starts injecting reactive power. And then what happens here when you do that, you can see that there is a lower fluctuation range. So it is able to reduce the magnitude of the fluctuations, but still there is a somewhat high voltage, right? So then in the third example, what they did was to combine. They kept the angle on, and they lower the tap, the LTC reference point. So by doing that, they were able to control both things. So smaller fluctuation range, and also lower voltage. So it's a coordinated solution. This is another topic that is important, and I think that this applies. It's somewhat similar to the analytics case that I mentioned before. Basically, what we have here is AMI. AMI has been around for quite some time. Over some of the early deployments, I think that happened probably 15 years ago, 20 years ago. And AMI used to be implemented only for meter reading, but now it is used for many other things. Capacity planning, DR management, outage management, for a variety of things. And that is happening with data in general. Another concept very popular in the US is microgrids. Basically, since we have distributed resources in distribution feeders and substations, so add the intelligence, the control systems that are required to allow the islanded operation of those grids, and also the implementation of advanced distribution management systems, which are basically the brains behind the operation of the grid, and they are analogous to energy management systems that we use in transmission. And the vision is something like this, basically, to have a collection of microgrids in the distribution grid. I don't think that this vision is going to apply to every single feeder, but in selected areas, I think that is going to be this way. And then the possibility of collaboration between microgrids, or to think about black start of distribution feeders, right? And then the concept that you guys are using here in Luxembourg, the community energy storage concept, right? You deploy energy storage on the secondary side of service transformers, and to be able to isolate the grid during events, and also to be able to interact with the grid, to provide services to the grid, the concept of virtual power plant, to do it in a coordinated fashion. Then EV adoption, I mean, we can talk about this for hours. EV adoption is very important. The challenge here is if utilities don't either control or provide incentives for charging at specific hours of the day, then what may happen is that peak demands in a service transformer level, feeder level, substation levels can increase significantly. It may not be across the entire service territory of a utility, but in specific locations, clusters, it may happen. And then that will require making investments, but the issue is that you may increase capacity, but that capacity is going to be used only for a few hours every day or every year. So what utilities are doing is focusing on time of use rates to incentivize charging, for instance, early in the morning. And that is actually beneficial, because what happens is now you're maximizing the utilization of your assets. Basically, you are increasing your load factor, right? But at the same time, it can be a problem, because in the past, going back to service transformers, they were designed with the expectation that they were going to be operating close to their maximum rating during a few hours every day, and then early in the mornings they were going to cool off, right? And then heat again and cool off, and to go through that cycle. But if they are permanently loaded, that means that could affect life cycle, right? So there could be some implications that is necessary to study. But yes, very important understanding how to plan the grid with electric vehicles. And going back to planning, to move from what I call a snapshot planning, which is the traditional way to plan the grid. Basically, in the past, when we used to plan the grid, we used to focus on, okay, let's make sure that we are able to supply peak demand. And then peak demand happens, 1 hour every year. And let's focus on, let's see, feeders and substations. what happens downstream, it doesn't matter. I mean, if we know that there are some service transformers that may be overloaded, yes, we'll take care of that. But it was snapshot in time, and the focus was very narrow to some key assets. The transition is now into high resolution from the point of view of time, temporal resolution. So instead of focusing on 1 hour of the day, let's look at every single hour, 87, 60 hours of the day. Why? Because now we have DR, and overloads may happen not only one time, they can happen along the year. So that's one thing. And then the other one is a spatial granularity, to look at every service transformer, every line. So it's a more detailed approach to planning. Another important aspect is the convergence between transmission and distribution planning. In the past, both activities were completely, almost decoupled, I would say. The outcome from distribution planning was an input for transmission, and that was it. But today, you notice in some of the early slides, there are reverse power flow through substations. So what happens in distribution affects transmission. So utilities are starting to think about, let's plan both systems together, and let's consider those distributed resources as a potential source or as a potential input in our integrated resource planning. And let's look at operations as well, because now when there is an event in transmission, for instance, an event that causes a low voltage in the transmission grid, that low voltage may also impact the distribution grid and may cause the trip of distributed resources. So that's the concept of low voltage or low frequency right through that now distributed resources have to be ready for. So DR readiness is very important, and in DR readiness we look at all of those and those different aspects. This is another example of what I was mentioning before. Another substation, in this case, is in North Carolina, just to show you that, yeah, this is real. And we have been looking at active power flow only, but we also have to look at the reactive power flow as well. So that complicates things, right? And these are some of the new leading practices in the industry, the DER hosting capacity that I mentioned before. This is publicly available. You can go to this website. You have to check. I know that I can access that website from the US. I'm not sure if you can access from Europe, but basically this is Washington, DC, and this shows the hosting capacity, the amount of DR that you can interconnect to every feeder in the service territory of PEPCO. PEPCO is the local utility in Washington, DC. Let's see if I recognize, I think a national mall is this area right here, where the Capitol and the White House and the Lincoln monuments are located. It's in that area. So hosting capacity is something that you, oops. Oh, okay. Hosting capacity is something that you can calculate it in several different ways. Generally, we look at thermal limits. When you add DR to the grid, you have to look at thermal limits of distribution lines. And also you have to look at voltage levels. So typically that's what we consider, but more recently we are considering also impacts in protection systems, impacts in reliability, safety, and others. Okay, so all of that is wonderful. Yeah, all of that is wonderful, right? I'm almost done. But the challenge is, who is going to build this grid? So that's all of you, right? The challenge is that we are experiencing a shortage of talent. And this is just for the US, but I think that is probably similar here in Europe. This is the number of graduates over the last 50 years in the US in electrical engineering. and different degrees, bachelor's, master's, and doctorate degrees. Now let's look at mechanical engineers right here. You can see that more graduates from mechanical engineering, right? Electrical has remained relatively constant. And now let's look at IT. So that's where they are going, to IT. Hopefully, now that the power industry is cool, finally, hopefully in the future, some of these folks are going to join us to build that grid of the future. And just keep in mind this, that what we do is really cool and it's vital for our global future. We continue adding renewables. We are going to add electric vehicles. Binary is changing. The billion-dollar events that I mentioned before, this is just a summary of those billion-dollar events for 2021. I was looking at 2023, and I think that there were like 27 billion-dollar events in the US only. When you look at the entire world, I mean, there are so many of it. So again, somebody has to build that modern grid. The economic impact is significant, and resilience, besides grid modernization, resilience is very important. And resilience involves cybersecurity as well. Those cyber events are also increasing. This was interesting. It's a comparison of one specific type of cyber event. And this was during the pandemic. I think that people probably had more time, too much time in their hands. As an IEEE volunteer and professional of this industry, I mean, we do this because we want to help people. And I really liked what Lucian mentioned about the fact that there are still millions of people who don't have access to electricity. So, so as engineers, that's part of what we do, right? Some of these technologies that we are developing are going to help those folks as well. And my final slide, I think that the key message is that, well, these are exciting times. The way I describe it is we are living kind of the golden age of electricity, right? It's like an age of discovery. And I see students in the room. So you all are going to build this this grid of the future. Hopefully this this presentation has been is going to serve as motivation to continue getting involved. And as you can see, there is plenty to do. And that's it. There are a few articles. And thank you for your time.
Thank you very much. So now we'll have a few time to discuss some of the topics of the presentation, and I would like to do this in a kind of a form of a informal, let's say, round table, where I would ask to join Julio. And thank you very much for your presentation. Really interesting material you put here, and a lot of stuff for discussing. So we for sure have a packed agenda until the end. I would like to invite Simeon Huxfield from the Ministry of Energy and Daniel Koster from LIST to join Julio here in front of the audience. And yeah, I'll just get the microphone. And this would give us the opportunity now to discuss some of the topics that Julio has just presented. So from my side, it was really, really interesting material that you put here. I was very pleased to see what the US is doing and to understand a bit comparing to what we know that Europe and the European Commission particularly is pursuing here. It's very good to know at what stage we are, and hopefully you can draw some lessons from what you do and what we want to do here. So I think one of I would kick off this with a question, then I would open also this to the public, should I have any questions to our speaker, but just as a way of kickstarting this. So you mentioned that the grid clearly is at the center of all these challenges of the clean energy transition, and there is an increasing need for strengthening the grid. So as we know, investments in the grid and this kind of building new lines, new transformers is a lengthy process. It's something that it's not easy to do shortly, but we have already very short targets for addressing electric mobility. We're talking about some targets that are already for 2030 or just a little bit after. Renewables again, and in Europe, you have to see this in the context of the Ukraine war and the crisis around energy that this has sparkled. So my question would be, for sure, we need to strengthen the grid, but will it be fast enough when we arrive there? What can you tell us about this? Is there something in between that we can do? There are talks in Europe around flexibility and this kind of things. I know flexibility is a broad concept, but maybe you could give us a few insights on that.
Sure. I'll give you my personal opinion, right? I think that some of the targets are too aggressive and probably not realistic. And that is a disconnection that exists sometimes between regulators or policymakers and then the industry. I think that the transition is feasible. We can do it. But I think that it has been, so going back to California as an example, that a renewable portfolio standard mandate, quite aggressive. And it was basically top down, right? It came from the government. The government said, we're going to do it, start working on it. Then the approach that was used in Texas was different. It was driven by the market. And both of them, both states, have reached more or less the same targets using completely different approaches. I was reading that I think that California is producing around like 37% of their energy comes from clean technologies. In Texas, I think that is around 33, but using completely different approaches. So I think that the way I see it is the only way to do it is through a collaboration between all parties. It cannot be, it cannot be top down. It shouldn't be also bottom up, just leave it to the market, right? There has to be collaboration. They have to sit down and then outline a realistic, I guess, plan, right? And realistic targets and goals, and then get to work. The other challenge that is a consequence of the pandemic and other things is, we were talking about it, supply chain. The fact that yeah, let's suppose that we sit down, we have the resources, and we sit down and we say, okay, this is what we are going to do. We're ready. We just have to build. And then you go and talk to manufacturers, and manufacturers tell you, oh, well, those transformers that you need, they're going to be ready in 5 years. So you have to consider that as well. And so manufacturers have to be part of that conversation. So a single stakeholder or just a couple of stakeholders working alone are not going to be able to make it. That's just my humble opinion.
Thank you. Maybe I take this opportunity to pass the word to Simeon from the perspective of, let's say, the government and how the states should really push this, how you see this problematic around grid modernization, what kind, let's say, of direction should we expect to drive us through this transition?
Thank you, and thanks for inviting. Thank you for organizing this event. I mean, the event series, but also particularly today's event. Thanks for the very interesting presentation, demonstrating the value of exchanging. Right? I mean, you always learn when you exchange, and I mean, there's some very pertinent and important takeaways that I, for myself, and I'm sure also the audience has had today. Following up on that, I think you said it all by pinpointing that what we do is cool and vital. I really like that. I must say, and I mean, just underpinning the importance. It's and speaking about objectives, really, because it's not only cool and vital. It's really, I mean, there's no real alternative, right? I mean, looking at the events globally in terms of climate change, but also related issues. lack of water and wars and really terrible things happening really pinpoint the importance of what we do, and we are part of the solution. And essentially what you also said, I mean, that's kind of a broader takeaway that I noted is that a lot of technology is there and solutions are there, right? So we can tackle it. There are means to tackle it. Of course we need realistic targets, fully agree, but this is where we need a bit of, how should I say, a bit of I mean, essentially coming together, discussing what's realistic, I mean, we all not only need to be realistic but also ambitious. I hope that is also common sense these days. And then of course you need to bring things together, and I think there was also an element of your presentation. I mean, it's increasingly about coordinating more and more market participants and a number of people, companies, businesses that participate in the energy transition and opt for solutions and install distributed energy resources, which by definition are smaller but more numerous. And you need to orchestrate and find ways how to make those things work together. And technology is key. Fully agree, and I think that was one of your key messages today. Digital solutions, but then also there's a social dimension, and I think this is particularly where also policymakers are in high demand actually, and need to do a good job to demonstrate the benefit of it, also for the individual. And then of course we speak about say the economic side of it, about subsidy schemes, about the cost of CO2 emissions, and those kinds of things, premium for electric vehicles and all that, but also about how should I say, maybe a narrative, a narrative why we actually need that and how the individuals benefit on the one hand side and can also contribute to the positive developments. And I think that's really where we are aiming to bring things together, also from a government perspective, with a number of initiatives. I don't want to dive again into the value of smart meters, which Luxembourg has successfully rolled out, and which I think is an important baseline for making certain developments work and feasible. Energy data platform, which we have triggered, all types of subsidies as mentioned already, but also new models that also have the social dimension enshrined, such as the community models that you also alluded to, and where LIST is very active in, covering the technological part, batteries, PV, etc. The economic part, of course, you need to somehow make it work also from an economic perspective. You need to find the money, and you need to have a certain return on invest in order to buy in people. But you also need really people to be motivated and to invest a bit of time and effort in order to make such projects work. So far from my side.
Thank you. Also, just before I pass this to the audience, just one question to Daniel. So in the context of this clean energy transition, the role of research, and especially I've been working with our grid operators, and you're working around also flexibility topics, which involve these two dimensions that Simeon was just talking about, so the technology, but also the social aspect. So maybe you could talk us a little bit about that.
Yeah. Thanks for the interesting talk once again. I think you covered a lot of topics. I think what we see, and what I partially also learned from European projects when you talk to utilities around Europe, that, I mean, finally, we are all facing the same transition, but we have quite different, maybe also levels of implementation regarding one or the other aspects, and the large variety of problems then also considering the different levels of implementation, put spotlight of different aspects of it. So if you talk to a utility in southern Germany, they will maybe come up with the same kind of curves that you showed of reverse power flows dominated by PV. If you talk to your Norwegian, they will come up with issues around high penetrations of electric vehicles. I talked to a Swedish utility company in another European project where they had quite some issues with high implementations of heat pumps nowadays, where they see the peaks completely shifting. So we see there is a lot of movements, and sooner or later we will face all these problems. And also our local grid operator, with which we are collaborating in a research project, sees these on different levels here, and is quite interested in ways on how to handle these flexibly, since we all know expanding the grids, putting copper takes long time, it's very costly, and are looking for ways on how to defer also grid investments, maybe at some hotspots at least. So we're looking into flexibility on more or less medium and low voltage level right now in the distribution, which could come from households, and the direct interrelation with the customers, with let's say their motivation, their behavior. That's something we're looking into there, and it's quite, I think, also challenging. We have been looking into, let's say, energy literacy on households. So people normally are used that the electricity comes from the plug. They don't really care, finally, what is behind this. But I think people are now more and more are also being interested, and we have always early adopters that are far ahead, but also the normal citizen at some point is trying to get more insights into this. And I think what is really interesting there is to see how we can manage to integrate normal people into that scheme, providing maybe flexibility without really harming their comfort. I mean, I think it's unrealistic to see that private households are, let's say, checking their smartphone once an hour to see if the electricity became cheaper or not. So that needs, I think, also a high degree of automation and smartness in the homes to make use of that kind of flexibility. So I think from my perspective, this is something we should invest also further insights into.
Perfect. If I may, I would open now also some questions from the public here, also the public that's remote. So you can ask questions in the chat and I can read them and I can ask the... Okay, so we have 2 questions. I would ask you if you please say your name, where you come from, and...
Hi, Jan-Philip Wassenaar, and I work in sustainability and carbon credits and that kind of stuff. I got a question. I saw a promising chart that there's now, well, millions of electric vehicles being sold, and at, say, average 100 kilowatts a piece, that's a massive storage capacity. Do you see a vehicle to grid as part of the solution? And is there something the regulator could do, like make that capability mandatory for new vehicles in the future, and then maybe also adding a bit of functionality that the vehicle can take external signals from an optimization, cost optimization program to charge or not charge, depending on the price.
Okay. So yeah, I was smiling because we were talking about it earlier. So the short answer is yes. Absolutely, and it's part of the future. Vehicle to grid is actually V2X. That's how they are calling it now. Vehicle to home, to building, to whatever you want. Yeah, it is part of the future, and it's real. It's real. I'll give you a couple of examples. Going back to Texas, well, General Motors released the Ford F-150 Lightning, which is a beautiful truck. It's a pickup. In Texas, we drive large pickups. That's a stereotypical Texan, right? So it's a vehicle that is a commercial solution. I mean, you can buy it. Actually, when it was released, it was sold out in a matter of days. I think that it's in backlog now, in production. Going back to supply chain, they also have some supply chain issues. And there were some success stories already. That vehicle has the capability to supply your home if there is an outage. You can plug it to your home and use it as backup generation. I mean, it was sold, one of the models in that vehicle, it was sold that way. I mean, the General Motors is commercializing it that way as a value added from the vehicle. And it was used, I remember the event that I mentioned 2 years ago in Texas, Winter Storm Uri, it was used, that vehicle to in some homes to supply service. So yeah, it is part of the future. I was recently, well, this past week, I was in Nashville in a conference. Utility Perspectives is a conference organized by Quanta Services, and with attendance from CEOs from utilities, from executives from manufacturers, and a representative from General Motors was there. And he was mentioning that, yes, it is absolutely part of their strategy in the US, and probably here in Luxembourg. I realize that is somewhat similar to the US in that regard. In the US, I mean, there is public transportation, but only in our old cities, which would be like New York and San Francisco and maybe Boston, Chicago. But in the rest of the country, you typically drive. You commute from home to downtown areas, and commute maybe 30 minutes, 1 hour, depending on where you live. So in downtown, we have parking decks. Sometimes an entire building is just used for parking. So think about it, eventually when we have the majority of those vehicles are electric, you have a big battery right there that can provide service to the grid. So yes, it is part of that future. I would say that 5 years ago, I would have had a different opinion, completely different opinion. But now that we see that it's real, yes, the consensus is that it's going to take some time, though, but we are going to get there.
I mean, also with respect to the question about the regulatory framing, right? So also clear, yes. I mean, there will need to be some regulatory framing for that. Standardization, I think, is very important, such as we did it actually globally for plugs of electric vehicles. I think that's really important for the industry to develop efficiently, or also from a global perspective, a competition perspective, etc. I mean, speaking about making things mandatory is always a bit tricky, yeah. But politics is following up, of course, on the developments, and there's working groups on an EU level dealing with this issue, vehicle to grid or even to X. So far, no, it's not a mandatory requirement, and I think we need to be a bit cautious with those obligations. I mean, it can be both. It can be an accelerator, but it can also be an obstacle, right? And I think as policymakers, we need to be a bit careful at that front.
Yeah, but it seems to be a shame to put 100 million EVs in Europe on the market and then say, well, it wouldn't have been great. Those things.
Agreed.
So that's it's really taken off. So you're missing opportunity there.
Thank you. We had another question there.
Thank you, Andre. Thank you, Professor, and welcome back to LIST. I'm Mohammad Iman Alizadeh from LIST. So as we have in our way to this clean energy transition, we know that we have different stakeholders in between, utilities, customers, government, so different entities. So we have here. So from your experience, because I know that from your background, you have this opportunity to deal with all of these in your work. So from your experience, who is lagging this? And from a company like LIST or the Quanta technology like yours, how can we approach to the lagging person, and how can we motivate him that look, you're lagging and you need to be updated from this aspect? Because from some aspects, the I don't know, the personality of data. So the data privacy won't allow us to access every data that we need to show themselves that you are lagging. So maybe they are happy with their current situation, but at least we as academia, we need to promote them and push them to higher levels that we think. Yeah, thank you.
So you put me on the spot. Let's see. I think that it's hard to say. It's hard to pinpoint and say, well, this is the stakeholder that is, as you said, lagging or preventing us from moving faster. I think that in all areas there is potential for enhancing things, doing things faster probably. So I'll give you a couple of examples. On the regulation side of things, just to give an example, let's see the framework, at least in the US, the framework to use third-party distributed resources as part of utility microgrids. So let's suppose that a utility wants to build a microgrid to improve resilience, reliability in an area of their service territory. So so they may do it, and they have done it by deploying assets that are owned by the utility. And but there are also assets that are owned by third parties or by end users that could be used as well. But that framework, that regulatory framework to regulate how that is done, it doesn't exist in some cases, in some jurisdictions. And the liabilities and those type of things, who is responsible for what, that doesn't exist at this point. And sometimes what I think and what I have heard is that sometimes the concepts and technologies go ahead of regulation. So I was talking about grid modernization, but there is also a need for regulation modernization in some cases, right? So that's one example. But then when we talk to in the case of utilities, of course, utilities have the responsibility to operate the grid, and they are liable if something goes wrong. You know, people are going to hold utilities accountable. So they tend to be sometimes very conservative in how they move forward. So so that's another example of something that may need to improve. Perhaps a little bit more flexibility to update processes and internally within utilities. So that could be another example. So it's a different stakeholder. Regulator is one, utility is another one. So I think that is a combination at the end. Everybody has a little bit of responsibility, and that goes back to my point that if we want to make the transition, and if we want to be ambitious and to your point, right, be ambitious and be realistic as well, all of us have to work together. I don't think that there is a silver bullet to do this. Everybody has to work as a team. It's the only way to accomplish it.
Okay. Any more questions from the audience?
Good afternoon. I'm Julia. I'm an electromechanical and energy engineering student. And I would like to ask you, because in my case, I have only an academic background. I didn't enter yet in the society. So I would like to ask what would be the best advice for a student like me, very ambitious. So I'm expecting maybe an answer from three of you, or only one, whatever.
Well, I'm going to give you my humble opinion, right? So, and this is just my perspective. So, I think that, of course, at the end, you have to make your own choices, right? So I'm just going to give you my opinion. I think that this applies to anybody who works in academia, and students, professors, etc. Anybody who works in academia. I think that it's important collaboration with the industry. So in your case, internships, it can start that way. Choose an area that you like, and then do an internship summer. I don't know how it works here in Europe. In the US, it's very common to do summer internships. 3 months or 2 months during summer, and get to work on real stuff, on applying that knowledge that you develop in school, or that you acquire in school. And then so with my colleagues from academia, I always encourage that collaboration. Actually, at Quanta, we do a lot of that, collaborate with academia, with typically when we apply to grants from the Department of Energy, is usually a partnership between a consultant, a university, a utility, and a vendor. So it's a really good, it's a very strong partnership. So yeah, that would be my advice, that you you learn how life it is, in the industry, and if at the end you decide to, for instance, if you like academia more than the industry, that's wonderful. But you have that connection with the industry world. That way, when you develop solutions, they are going to be applicable. That would be my advice.
I may add to that. So first of all, what I mean, as we heard, what you do is cool and vital, right?
Yeah.
So you shouldn't worry. Yeah, it's you'll find something. I don't have any doubt. I mean, really subscribing to what you said, and I mean, at the end of the day, I think you will have a certain benefit in the sense that you can actually choose what you would like to do, and I mean, my advice would be to actually make use of those options that you will have, and think about where you want to be and where you can have an impact with what you do, and that can take different angles, of course. I mean, it can be more technical, it can be more on the, say, economic side, developing businesses. It can be on a political side, rather going towards the regulator or the ministry. So there are many different angles to energy, and I think that's actually what makes the field so exciting. And I mean, there are many opportunities that you will have. So rather a challenge of identifying the best one, and indeed exchanging with people is typically a good way forward to see and learn what you like best.
Maybe Daniel, to finish off, just because List is also in a position right between academia and industry, so it's kind of the middle ground here. So maybe you can offer your perspective, and then I will come back to you with another question.
Yeah, maybe a lot of things have been said already, so I guess, but what became also clear also from your presentation is that this whole energy topic becomes very diverse, also multidisciplinary, and that it's very important, I think, to stay interested and have an open look into all these different disciplines that are interconnected, because I think, I mean, yes, we will still need specialists also in the future, for sure, but having this open perspective to the left and right, I think is very important. Not only the technical one, but also the economic side of it, the policy side of it, maybe. And there, somewhere in between, you might find the way where you say, this is where I find my passion, and this is always the best driver and motor for the energy that you will need throughout this long trip. So find where your passion goes. And yeah.
Okay. I'll just stick with you for one more moment, but just taking one thing that Julio had in his presentation, I think really created an impact on us. So the duck curve, and how fast in 8 years we came from that figure there to really reverse power flows by 2023, and this canyon curve. So the point is here, is technology helping this? How can technology help this? What kind of solutions? I'm thinking storage. What kind of storage? What degree of storage should we consider? So can you maybe elaborate a little bit on how you see some solutions to get out quickly of this? Because again, as we mentioned before, the grid will not be ready for until a couple of years, but we need to act now, because this will create problems. It's already creating problems, and it will create more and more problems soon. So maybe you can start with you, Daniel, and then pass.
Yeah, that was also one of the slides that really I was surprised and amazed specifically by this very short amount of time, and considering the long planning perspective of a grid and seeing these drastic changes in a short amount of time, that's something that does not really fit together. Storage, yes, I think that could be one potential option, but the way I see storage currently implemented, which is more small scale storage, at least what I see in Luxembourg, what I see in Germany also, PV battery systems owned by the private, the people operating the PV systems, helping their self-supply is a way of operating that does not help actually with the grid. The battery will be full, I don't know, around noon, and then still the full power goes into the grid. So what we would rather need is storage, if it's storage more on utility scale maybe, or an energy community scale, a little bit larger, with also different business models behind that bring more this grid relieving way of operation and perspective to it, but not having purely, let's say, this very self-centric perspective on optimizing my own consumption only. Just a
I take it further and you wrap it up. I think the challenge is not to jump too quickly to one silver bullet, as you call it, because we won't have it anyways. I mean, the challenge that we are faced with as policymakers is to set the right framework to make the system develop in an efficient, safe, and sustainable way, right? And I think the duck curve is a perfect example. And I mean, you could, and that's kind of my perspective. I mean, at the end of the day, you will need to have a certain regulatory framework that allows other technological solutions to pitch in based on these developments in order to complement it with something that is most efficient, right? And batteries will have a case in a system that is more and more volatile, because that, I mean, when you let the system signals unfold their effect, and I'm speaking mostly of price signals here, I think this will create a case for alternative solutions to come in and complement those developments. Of course, there needs to be an overall development which is largely driven by policymakers, setting ambitious targets, as discussed already. But then in order to find the right technological solutions and business models behind, I think we shouldn't aim for something that is administratively set. I think that's an illusion. So we won't find the golden rule where we would say, okay, we know how to solve this, but it's really up to businesses to create technical and economic solutions that pitch in and complement these developments. And if there is a duck curve and lots of energy available, that will lower the value of the energy at this specific moment in time, and it comes back to a high value when you reach, when you go out of the belly. And I mean, this is sort of the system perspective that I think will be crucial. Once again, orchestrating different resources and facilitated by a regulatory framework, allowing those technologies and businesses to unfold.
You
want to, yeah,
if you want to wrap up.
Yes, and I was looking on my cell phone because I wanted to make sure that I remembered a date. So it is related to the conversation. Let me explain. In 1962, President Kennedy, John Kennedy, he visited Rice University in Houston, and that's where he delivered that famous speech about we choose to go to the moon not because it's easy. So that was 1962, and 7 years later, that was accomplished. Think about it. In 7 years, that was a major development from a speech to make it a reality in 7 years. So I mean, if we were able to do that, yeah, we can do this too. The energy transition is feasible. Now, again, there is no silver bullet, so it's going to be a combination of solutions. So energy storage is part of one of those solutions, and perhaps also recognize that there are intermediate steps, right? And so in those intermediate steps, they can be, for instance, in the US we call natural gas as a transition technology, right? It's a transition technology. We may need it for a few more years to while we develop some of these other solutions like long energy storage, right? So again, this is going to be work that you guys are going to do. And if we were able to go to the moon in 7 years, probably we're going to be able to develop some long duration energy storage solutions in 7 years or 5 years or whatever it is. And another one is, at least in the US, we're looking at modular reactors, nuclear reactors. I know that it's different here in Europe, right? But in the US, that is also a potential option, and it's being supported by the Department of Energy. I think that it was last year, if I'm not mistaken, that the first design for a commercial modular nuclear reactor was approved. So there are a few companies that are working on that. And then I fully agree with you about the behind the meter side of things, being able to optimize and add flexibility to the grid, and again, maximize the utilization of assets, being able to operate microgrids and nanogrids, and focusing also on the consumption side of things, or now we say prosumer, of course, but focusing on the behind the meter side of things. I think that's very important. But at the end, I think that yes, it's a combination of solutions. It's a portfolio of solutions rather than a single, silver bullet. Yeah.
Okay. Thank you very much for wrapping it up and for taking us home. I think it's more or less time that we finish. I just want to thank our speaker today and the panel here for the nice discussion, and thank the audience, both here as remote. And thank you for joining us. I hope to see you next time in the next lectures. And for those who were brave to stay until the end, we have some drinks and something to eat after. So thank you very much.
Yes, I will.